Guys, welcome back to the channel. Here we got another breakdown. My name is Eric, and for those that don't know me, for those of you that do not know me, my name is Eric, and I'm on a mission to help make sure that you guys have this MCAT exam easy as possible for you guys. Okay, you're a pre-med, you got a lot going on. All right, this MCAT shouldn't be this huge, big obstacle. You know, MCAT is easy. A lot of you guys been programmed, or a lot of you guys been strongly believe that the MCAT is hard when it's really not. Okay, if you do what I tell you to do, you know, on how to highlight, on how to pick the best answer choice, how to, make these things make sense, on how to read this passage. If you do what I tell you to do, this MCAT is going to be a piece of cake for you, and you will hit that 132 score. I promise you. All right. So I'm going to be breaking this down. I'm going to show you guys exactly everything that needs to be done. I'm going to show you guys how to highlight, how to pick the best answer, what to do if you're stuck between two answer choices. I'm gonna make sure everything makes sense for you guys. All right, so as always, before I break this down, do the passage, read the passage, do the questions on your own first, and then play the video and hear me break it down. Okay, it's important for you guys to do this on your own first. So I'm going to scroll down, pause it whenever you need to, read this passage, guys. All right, and answer these questions on your own. So this is 18, 19, 20, 21, 22. Okay, and I do these live for you guys. I don't screenshot this like other YouTube channels, okay? I don't screenshot this and put it in a nice doc and go through it first. And then, no, this is live. I've never seen this before in my life. Okay, I'm gonna show you guys how to get them all right. All right, and at the end, over here, I have the answers. I have not looked at it yet, so we're gonna see what the answers are. All right. Here we go. Ankle sprains account for nearly 15% of sports injuries. The basic mechanism of an ankle sprain is a bend of a ligament in a direction approximately perpendicular to the long bones of the leg. Also, guys, the pace that I read this passage is the pace that you should be going at as well. Okay? It's a regular pace that's a little slower to make sure you really understand all the details. Okay? So the reason why I highlighted this, this struck out at me. You highlight anything that strikes out at you. That's how it is. Okay, what strikes out at me may be different than what strikes out at you, and that's fine. Translation of the talus relative to the tibia beyond what is physiologically allowed by the tissue in ordinary movement is the immediate cause of a sprain or tear. Okay, I like that. That makes sense. Not too crazy there. A translation of 6 millimeters is the upper bound of the ordinary deformation of the body, though this number may be lower in some individuals. The anterior drawer test can be used to measure the degree of translation. All right, and they give us a figure here. We don't look at the figure. We only look at the figure when the question asks. If not, you're going to waste your time. Don't waste your time. Come on. The Taylor tilt test can determine the normal Taylor stability or range of motion for a given individual. Okay, I highlighted this to give me a quick reminder. Boom, Taylor tilt test determines the range of motion. Cool. In the test, the patient is seated comfortably while the examiner gently inverts the heel relative to the tibia. Okay, the resultant angle between the dome of the talus and the tibial plafond, see figure 1, is measured, with the maximum angle of 5 degrees being most typical, though anything from 0 to 23 degrees is possible. All right, so they twisted this ankle and they saw, all right, if I can go 5 degrees, that's typical, that's fine. If I go 23 degrees, that's possible, that's fine. But if I go way beyond that, then there's something wrong. Okay. The standard Taylor test has a degree of subjectivity and is not as quantifiable as a new approach that uses mechanical isolation of the joint. Okay. Let's see what this is, this mechanical isolation. By applying the force via mechanical stirrup and combining the Taylor tilt test with the anterior drawer, consistent values have been measured. I'm not really sure what a mechanical stirrup is exactly, but that's fine. Okay, I know that they combined this with the tilt test, and from there, they were able to obtain values, obtain data. Cool. For an anterior force of 98 newtons, and a torque of 13 newton per meters, the mean Taylor tilt translation was 48 degrees, and the mean anterior drawer translation was 5.7 millimeters. All right, whenever you're given data like this, guys, like straight up like 98 newtons, 13 nanometers, 48, 5.7 millimeters, whenever you're given data like that, you can highlight it. It's fine. Okay. The question will usually ask for it. All right. 9 times out of 10. It's fine. Anterior forces of 500 newtons or higher lead to abnormal translation and result in injury. Boom. I am highlighting this. Okay. Injury. Something impactful. A big event is happening, guys. This patient can get injured if forces of over 500 newtons happens. Whoa, injury, whoa, pops out. Highlight it. The question will most likely ask about it. Most likely, okay? This can occur when a person is carrying a larger load. For example, individuals who are overweight or obese. Okay, so if you're overweight or obese, you're more likely to twist your ankle. That makes sense. More common is when the ankle is subject to stress upon landing from a height or turning at high speed. Injuries may also result from smaller anterior force values if the torque is sufficiently high. Okay, so the torque is very important. If we have that high torque, boom, we're going to break our ankle. All right, not too bad at all. This passage, I would say it made a lot of sense. For me, it made a lot of sense, okay? I know I'm going to have some physics coming up. I already know I'm going to be bombarded with physics, but we got it. Have confidence in yourself. You guys can do this. During the force test with the mechanical stirrup, at what distance from the ankle joint was the force displaced? Okay, let's look at the mechanical stirrup. Let's look at it. Okay. What do we have here? We had a force of 98 newtons, a torque of 13 newton meters, and the 5.7 millimeters. Okay. Now, what is going on here, guys? What distance from the ankle joint was the force applied? If I see this is giving me information about torque. All right. We have force and we have distance here. All right. They give us the torque. They give us the force. So we just kind of have to find the distance. That's it. All right, so I'm going to use the whiteboard so it makes a lot more sense for you guys. All right, so torque is equal to R times F sine theta. All right, how did I know to use this equation? How did I know? Well, I looked at the question. I hanged on to every word in the question. What are they asking? Distance from the ankle joint that the force was applied. Okay, distance. Ankle joint with the force applied. Okay. So, sine of theta. Remember they told us it was perpendicular? Okay. If it's perpendicular, it's 90 degrees. Sine of 90 is what? Sine of 90 is 1. Okay, it's 1. So I can just leave 1 here. The torque they told us was 13 newton meters. 13 newton per meter equals R, which is the radius or distance, which we're looking for, times F, the force, which is 98 newtons. We got everything we need. Divide by 98, divide by 98, 13 divided by 98. I'm going to round this to 100. This is equal to 0.13. Okay, 0.13 meters. Oh, and they want millimeters. Okay, so I'm gonna go 1, 2, 3, 130 millimeters. All right, and that's close to D, 133. Bam, that's how we do it, guys. Do not be scared of physics. Do not be scared of physics. During the anterior drawer test, the joint translation occurs in 0.2 seconds. What is the average velocity of the talus during translation? Okay. Let's use our units here. All right. Nope. Okay. What we got here? Write down what you know. Write down what you know. They gave us time. 0.02 seconds. Okay. They're looking for a velocity. Well, I know that velocity is equal to distance over time. I have the time. Okay, I have the time, which is 0.02 seconds. Do I have the distance here? Okay. let's look at the anterior jar test. Let's see what happens there. Okay. Where is it? Oh, it's down here. Hold on. I think it was they gave us here. Okay, I'm sorry. 5.7 millimeters. Look, anterior jar translation was 5.7 millimeters. That's also the only distance they give us in this whole entire passage. That's it. That's the only distance they give us, so it has to be that one. All right. Cheat sheet. Equations are a cheat sheet. So what is it? It's where is it? 5.7 millimeters, which is 5.7 millimeters, which is 5.7 times 10 to the negative 3 meters. This is 5.7 times 10 to the negative 3. And I don't like this, so I'm going to do 2 times 10. 0.02. That's very low time. Is it 0.02? No, it's 0.2. Whoops. Okay. 0.2. So this is 2 times 10 to the negative 1. Okay. Boom. Lars. When we go to the right, we subtract. So 2 times 10 to the negative 1. And this is equal to, we got negative 3 minus negative 1. This is 10 to the negative 2 times 5.7 divided by 2. What do they give me here? 2.85. It's definitely 2.85. So 2.85 times 10 to the negative 2. Bam, it's B. You already know how it goes, guys. Don't be scared of this physics. If a 65 kilogram man undergoes a turning acceleration of 5 meters per second squared during a running turn, what is the magnitude of force experienced by the foot due to the ground? All right. Oh my God. All right, this is a good one here. That one made me cough. All right. If a 65 kilogram man undergoes a turning acceleration. Oof. All right. This is what's happening. All right. This one's a little tricky. Okay. This guy is running. Okay. He's running. He's running. He's making a turn. And we have to assume perpendicularity here. Okay. So he's turning hard like this. Boom. Just like that. All right. And his shin, or not his shin, but his long bone on his leg, it wants to go this way. All right. It wants to go this way. All right. So we can make a triangle here. All right. This is perpendicular like that. Now I'm going to make it like this, the triangle, to kind of make it make more sense for you guys. All right. His shin wants to go this way, but he's turning this way. And they're asking, what are they asking for? The magnitude of force experienced by the foot due to the ground. So the ground is the hypotenuse here, pushing it back. Okay, the ground is kind of stopping it from going there. All right, that's what's going on here. It's hard to picture. I'm gonna say that this is probably a very, very hard question here. Okay, but now we got to find out, what do we put in these values for? Okay, so this is the hypotenuse. This is one that we're finding. We're finding this. His shin going over there can be what? Well, turning acceleration of 5 meters per second squared. Okay, so the turn is 5 meters per second squared here. So we have 5 meters per second squared times what? Okay, we need to know the force here. Well, force equals m times a. We have the a, we have the mass, which is 65 kilograms. It's a heavy boy, big boy. All right, and the force, his shin wants to keep going this way, and his shin, his body, is made out of what? What's the force of the body going? Okay, the force is m times g. All right, it's the weight of his body. That's what's pushing it this way. This guy. So remember how I said he was running? Forget that. He was standing still. All right. And then he accelerated. Okay, to make it make more sense for you guys. So his body weight is what wants to go this way. All right. So this is his body weight. It's going to be 65 times 10, which is gravity. So this is going to be Pythagorean theorem here. 65 times 10 is 650. All right, squared plus 5 times 65, which is 5 times 60 is 300, 325 squared equals c squared. Okay, a little sloppy here. And then we got to solve this. This can be 700. This can be 300. All right, 700 squared is, I'm going to write this on my paper and make it a little easier. All right, we had some technical difficulties, but we're back. All right, so 700 squared. If you guys want to do the math, I'm going to have a calculator here, so I'm just going to do that. That's 490,000. Okay, plus 300 squared, 90,000. Okay, and then 490,000 plus 90,000, 580,000. Square root of that is 761. All right, if you guys want to do the math, you could, but for the sake of this video, I'm saving time. I'm sure you guys know how to do that. So 761, so the answer is C here. Hard question. That's a hard question. It's a little unfair, that question. They could have made it, that's a little unfair. They could have made it a little easier in my opinion. Which of the following is most likely to result in ankle injury? All right. A 700 Newton normal force exerted by a flat horizontal surface on the feet. Normal force is this, guys. It's a straight force going up. Let's say a box is on a table. Normal force is this. Gravity is this. All right, it's that simple. That's not breaking anyone's ankles, okay? A is wrong. An interior force of 450 newtons at the pivot point of the ankle. Okay, but they told us that, I think it's 500. Yeah, you need 500 or higher to result in injury of an interior force. So this is wrong. A 900 normal force exerted by a flat. Again, normal forces are not going to do much here. That's not going to break your ankle. All right. We need that rotation. We need that torque to break the ankle. An interior force of 400 newtons at a distance of 10 centimeters from the pivot point at the ankle. All right. Yes. This is giving us that torque. Oh, injuries. Also, look, injuries may also result from smaller interior force values if the torque is sufficiently high. This is a sufficiently high torque. Okay, I'm sure if you do the math here, it's going to be over 98. Okay, like 400 times 10 centimeters into meters is like 0.010 meters. All right, and then you go at, actually no, 0.1 meter, and then 0.1 times 400. Yeah, that's going to be over 98. Okay, so answer is D here. According to the passage, all the following are true about ankle injuries except they are more likely to occur in individuals with a very low body weight who have been unable to build up ankle strength. That is wrong. They're more likely to occur in obese people, remember? That was in the passage. A 13 millimeter translation of the talus relative to the tibia will cause injury. Maybe. Let's see. What do they tell us here? Let's keep going. An interior force of less than 90 newtons does not typically result in injury. That is true. Oh my God, guys, I'm messing up. I'm sorry. Yeah, that's true. An interior force of less than 98 newtons is not. That is true as well. That's true as well. Oh, they're asking for except. My bad. So this one's right. All right, guys. That was it for this passage. Honestly, that physics question was a little unfair. Not gonna lie. It's okay, but it's that's a very hard question. It's very, very hard. So don't be upset at yourself if you got that one wrong. All right, as always, guys, go ahead, comment down below. Let me know what you guys think. In the comment section, I have a link. If you click on that link, you will have a chance to go on an interview with me, and I'll see if we're a good fit so that you can go ahead and join MCAT University and make sure you hit that target score. Okay, it's very affordable for you guys. I made sure of that. So if you're interested, go ahead, click on that link, and I'll see you guys in the next video. Next video, we'll be doing passage number 5. We got all of it right. So here was D, we got this one right. Here's 19, we got this one right. Here's the explanation if you guys would like. Let me scroll down. Oh, that was a long explanation. Here's 20. C, we got that one right. And here's the explanation. This was the, honestly, in my opinion, the unfair one. Okay, look, only 9.4% people got that right. So you already know. All right, difficulty highest. Hell yes, the highest. 21, D, we got that one right. There's explanation. And 22, hey, we got that one right. All right, cool.